Right, so let's discuss the yet another geometry, which is the cylindrical pipe flow. Or we can just say pipe flow in this case. Okay, so in this particular case, we are going to consider the flow through the pipe. And then let me give a schematics here. So here's a pipe. Usually the pipe, we are going to give this, the pipe geometry. So let's define the coordinate along this pipe is a z. So within this pipe, we have a fluid of the rho and mu, and then over the distance of the L, we apply the delta P to bring the fluid forward. In this case, okay, pressure is the applied from the left to right. And then let's also consider this diameter of the pipe is a d. Okay, so we can also consider this d is also 2 times the radius. This is also fine. Okay, so this z is the along the pipe. Okay, along the pipe. Right. So given this, right, okay, pressure applied to the pipe, okay, in this case, we can have a same argument, pressure along the pipe, okay, which is the dp dp dz is equals to delta p over L. How this p is going to change, this is linearly decreasing, just like other Poiseuille flow, and then this is supposed to be decreasing. Okay, this is the setup. Okay, so it's a linear pressure gradient along the pipe. Okay, and then this is also this assumption is really the reasonable because pipe doesn't have a different geometries at the different locations. Okay, so in fact, with this, let's try to analyze this particular flow by using the Navier-Stokes equation. Okay, so in this case, okay, let's just use the cylindrical coordinate, which is the r, theta, and the z instead of the Cartesian coordinate. Cartesian coordinate, which is the x, y, and z. Okay, so if we take a look at here, it's going to be, it's really, we are looking at the cross section. Okay, perhaps the just for the sake of the argument, okay, I can still define this, this is the direction of the z, but when we have this Cartesian coordinate, sorry, it's a cylindrical coordinate. We do have a different axis here. Okay, this is the radial axis, which is the along the this in the direction of the radius. We also have the this angular direction, which is the along the at the different the angle in the circle here. Okay, so the in this case, right? If you take a look at here, again we are going to do the similar things, but the if we take a look at the this particular fluid, okay, so this is a cross section. So Cartesian coordinate, when we look at the Cartesian coordinate, if we look at this B, we had this U of the I plus B of the E J plus W of the K, right? This is probably, this is how we did it. But in case of the cylindrical coordinate, we can also define this, the V as the following. This is the V of the R in the direction of the R plus V of the theta in the direction of the theta plus V of the Z in the direction of the K. Okay, in this case, we can also write the W, but just to distinguish, we just wrote in this, the three directions. Okay, so in this case, the meaning here is the, if you take a look at, the particular cross section, and then let's say we have a fluid particle here. Okay, let's say we have a fluid particle here. This, the V of the R is the direction from the center, considering from the center, there might be some velocity, right? Which is this is the V of the R. Okay, and then if we take a look at this is the this geometry, okay, for the direction that's going to along this, the angular direction, this is the V of the theta, right? And then, the B of the Z is really easy. Of course, there is, the also the for any kind of, the fluid particle, that also should be trying to flow in the direction of the B of the Z. Okay, so this is, these three direction is the really about the B of the R and the B of the theta and the B of the Z. And then R hat, theta hat, and the K hat are the unit vector. Okay, so the in each direction. Okay, so this one is like a IJK. Okay, unit vector in each direction. Okay, so this is all right. So let's just do the following. Okay, we are able to follow the same idea. Okay, of this solving Navier-Stokes equation. Okay, we can take the same steps. First step is the postulate the solution. So let's try to postulate a solution. In this case, okay, really, okay, I'm going to write this. This velocity vector can have a different component. This VR going into the radial direction of the in the V theta into the theta direction, and then B of the Z in the along the pipe here. Okay, so in this case, okay, the which one is the really the reasonable which one is the zero? Okay, so in fact, the something that we can observe here is the there shouldn't be any radial flow, right? No radial flow. And then this assumption gives us the this VR equals to zero. Of course, those fluid particles do not try to go the outside, right? So this VR is zero. Also, similarly, no angular flow. No angular flow, which this assumption really gives you this V theta also equals to zero. And then, the flow through the pipe, flow through the pipe is this is existing. Okay, so in this case, B of the Z equals to this is the value which is non-zero. Okay, so this is really this assumption this is it makes us allow us to simplify this equation a lot. Okay, so this BR is probably this equals to zero. No radial flow. This V theta is no angular flow, it's 0. And then this is the flow along the pipe. So that makes sense. Okay. So this is really help us to simplify this. Okay. So just like the in the other cases, in the Cartesian coordinate cases, in fact, flow can be reduced into the just a single direction, which is the b of the z of the k. Right. So this is great. So then the next question is the what variables? Which variables does b of the z depend? Okay, so this is the same question as the other cases. Okay, so in this case, okay, this b of the z is the b of the z of the four variables. Instead of x, y, z, in this case, it should be r, theta, and z, and t. Okay, so this is really, they try to extend the argument. Okay, these are the three variables about the location, and then this is about the time. So this argument is quite similar to the argument is quite similar to the what we had for the Cartesian coordinate. So let's make a few different, the cases here. So first cases is the let's assume the steady flow. If we assume the steady state, there is no time dependence. This is probably fine. And then if we look at pipe, right? Okay, so now the if we want to take a look here, so if you compare this location and then this location, which is at the different theta, right? So let's say this is the theta 1, theta 2, theta 3. Okay, does this really gives the different speed or different rate? Probably not, right? So it's no dependence, no angular dependence. Okay, so the which means the theta is the no theta is not a variable. Okay, or the we can say the speed doesn't depend on the different location in the different angle, right? So that's probably the case. You can also consider the if you compare this location at a different location along the z, they are probably same. Okay, so this is you can say no z dependence. Once they reach a steady state, then they just go straight uniformly, right? At the uniform speed, so they are not going to be dependent. Okay, so just to be they describe it in a consistently, we can say no theta dependence, no z dependence. Okay, so and then lastly, what can you say here about the radial location? So this is a similar argument. If you are comparing, okay, this is the center of the pipe. If you are comparing the fluid particle at a different location, you consider this one is the let's say this is the R1, R2, and then R3, right? If you compare these three locations, probably we can probably assume the speed is lower if it is closer to the wall. Okay, likely speed is lower when the fluid particle is closer to the wall. Well, it makes sense, right? The just like the when we had the Poiseuille flow for the between the two plate, the when we had the location, flow when flow is closer to the wall because of the no slip, they receive the higher shear stress, and then they sort of they do not they achieve the higher flow rate. So it's most likely this is the flow depends on the flow is going to depends on the radius. Okay, so this argument really tells you, okay, indeed, this B of the VZ potentially R, theta, Z, T are the four variables. However, no T dependence because it's steady. And then no theta dependence because of the symmetry. No Z dependence because it shouldn't, depends on the location, how much they advance. So this is the only dependence of the BZ should be a BZ of the R. Okay, so this is the our postulated solution. Okay. In addition to the B of the R equals to 0, and then B of the theta also equals to 0. Okay, these are the our postulate. Right. So based on this, okay, that's the first part. The second part is the let's check this solution with the continuity equation. Okay, so part 2. Check the postulated solution satisfies the continuity equation. Okay, so in this case, okay, steady flow of the when you have a steady flow, continuity equation is going to be nabla dot rho v equals to 0. This is the continuity equation. Okay. So one thing that we must pay attention here is the nabla is different in the cylindrical coordinate. Okay. So this is the nabla in cylindrical. So nabla in the cylindrical coordinate okay, is the nabla equals to this is the r ddr plus theta 1 over r dd theta plus k of the ddz. Okay, so they do have a different expression for the nabla. Okay, they do have a different expression for the nabla. So this is going to give you a slightly different continuity equation. Okay, so in fact, the continuity equation is going to be this nabla dot rho v. Okay, it's going to give you a different expression. So let me just, in this case, just give the expression. It's going to be 1 over r ddr of the rho r br plus 1 over r d theta times the rho b theta plus ddz of the rho vz. Okay, so this is the expression for the continuity equation, and then the postulated solution here that we have here is the b theta is 0, br is the 0, bz is the bz that depends on the radius. Okay, so this is our postulated solution. I'm going to skip a little bit here, but this is going to tell you this is going to be equal to 0, and then this is the this is equal to 0, and then this bz equals to bz of the r. So this is when you take a derivative with respect to dz, then it is going to be 0. So essentially, this is going to be 0. So satisfies the continuity equation. Okay, so this is great. So now, based on here, we can move on to the simplifying Navier-Stokes equations.